This talk presents a study of dark patterns in home Internet of Things devices. I'm Johanna Gunawan, and this is joint work with Monica Kowalczyk, Daniel Dubois, David Choffnes, Woodrow, Hartzog, and Christo. Firstly, why should we care about and thus study dark patterns in smart devices? For starters, IoT devices are popular tools that save time, help us multitask, and leverage the power of data beyond websites and apps. However, such devices are known to carry privacy, security, and consumer risks as a result of their ability to collect sensitive personal data at unprecedented scale. Next, dark patterns are potentially deceptive and harmful designs that interfere with our digital behavior to extract attention, money, and data, or otherwise push us towards unintended or undesired outcomes. To illustrate, such designs can disproportionately promote data-hungry options like account signup or cookie acceptances over the available alternatives by de-emphasizing those alternatives with creative button placement, size, or color. Our interdisciplinary team then wanted to ask how dark patterns might manifest in IoT devices, namely, what can we learn about them and what kind of harms are implicated? Overall, we found that multiple factors may influence dark pattern deployment and prevalence, and that these patterns can raise unique concerns for user finances, autonomy, and privacy. To investigate our questions, we interacted with smart devices in our IoT lab, which features over 70 devices in a fully functional studio apartment setup. This includes cameras and doorbells, home automation devices and smart hubs, home appliances like microwaves and fridges, TVs and media devices, health devices, and smart speakers with voice capabilities. Now, to handle this range of devices, we conducted preliminary tests with an initial 71 devices and then iteratively annotated each device according to existing taxonomies. From these pilot experiments, we developed an interaction script to standardize tasks that we would conduct across all devices, as well as a verbal script for interacting with voice assistants. We also built a codebook of dark patterns, appending new patterns that we discovered in pilot experiments. We also further categorized dark patterns by the types of interactions that they might appear in. One example of a new pattern we identified is a settings detour, in which users are prevented from accessing certain settings in the modality they're currently using and are instead asked to detour to an external location, as in this case from the Amazon Fire TV. This can waste user time, interfere with autonomy, and can subject people to additional privacy risks. So with these scripts and the codebook, we proceeded with our formal experiment, which resulted in recorded interactions for 57 devices. We did not restrict the time spent per interface, as we aimed to explore as much as possible per device, and this was in order to annotate both unique dark patterns as well as the overall frequency per dark pattern per device. This manual process took place over the span of several months, including intra-author review and iterative discussions throughout. So what did we learn? When accounting only for unique binary presence of dark patterns in devices, we found that the general interface interference patterns of visual preference and preselection to be the most prevalent, which were present in over 80% and 60% of all devices, respectively. The next most popular dark patterns were from interaction contexts that are common in most device or software experiences, like registration or settings management interactions. Then the vast majority of dark patterns in the codebook were prevalent in less than 30% of devices and thus less popular overall. For some extra detail, these are the top 5 devices by their dark pattern counts, and we see that the highest number of unique patterns found per device is 25, and the highest total count is over 3 times higher at 90 patterns. But we wanted to learn more about the disparity between these two counts, and since our interactions were not time-bound, we wondered whether feature richness, which means more features, options, or design complexity per device, could impact how many dark patterns we might encounter. Now, using the recording duration or interaction time as a proxy measure of feature richness, we plotted the device's dark pattern counts against this duration and found significant positive correlation. However, the distribution of these two counts differs. The total frequency count is more tightly clustered, with more devices concentrated around fewer total patterns or time spent, and the outlier behavior depicted by a long tail. Conversely, the unique count is distributed much more loosely at lower counts. More research is needed to understand the relationship between feature richness and dark pattern deployment, but overall, the positive correlation tells us that more interactions generally means more dark patterns. But to dig a little deeper, we look at dark patterns by specific device traits. As IoT devices require smart internet-enabled components, as well as the hardware and firmware components, we were interested in how these two modalities could impact dark patterns. So we categorized devices by the extent to which they required a companion app, and this resulted in 4 modality subtypes. Here we break down the dark patterns by the codebook contexts, and this immediately revealed some quirks, with the notable example in the advertising and marketing materials. So as shown here, the dark patterns in the ads context were relatively unpopular overall, and only found in less than 40% of 2 modality types devices. But in our codebook, we classified non-traditional, internal, advertising-like behavior under subverting expectations, as traditional ads are treated quite differently in the law and have disclosure requirements. So all modality types contained self-promoting nags and behaviors in the majority of their devices, but it was only the media devices, which did not require use of a companion app and were noted here in the orange device-only category. They are the only ones that contain traditional disclosed advertisements. To illustrate the difference, in this Amazon Fire TV media device, watchable content is provided in thumbnail carousels with content descriptions. In some carousels, we noticed that traditional advertising behavior in which sponsorships are disclosed. But we also saw those self-promotional internal marketing nags in these carousel descriptions. And in our case, we did not sign up for a paid Amazon Prime account and thus wouldn't have been able to access the Prime content marketed to us here. These types of nags subvert user expectations of what kind of content is actually available to them and can nudge people into eventually subscribing to paid services. And it doesn't help them differentiate what is accessible and what's not. So next, we were interested in how dark patterns differed across device types. And the majority of devices had about 20 or less unique total dark patterns, which is consistent with prior work. However, our scatter plot notes that significantly higher dark patterns were found in cameras, doorbells, and speakers. And one thing to note is that the diversity of devices within one type can range widely. Home appliances include fridges and microwaves, which are functionally dissimilar, whereas media devices, especially streaming ones, serve tightly similar purposes. And yet, within the media devices, we only see the Fire TV, which had high outlier counts of dark patterns and diverged from the others. And this makes us question why a device in a relatively homogeneous group might be so different from the others in terms of dark patterns, and we turn to the next device trait. Now, in this trait, we look at manufacturers, and a few of them are very well known, so we stratified the devices in our dataset by the manufacturers with at least 3 devices in our study. And in this box plot, we see that Amazon and Google are the ones with significantly higher total dark pattern counts than the other manufacturers. Now, note that both Amazon and Google produce cameras, doorbells, speakers, and media devices, which were the types that contained higher dark pattern counts in the previous trait. Now, this can seem alarming at first, but when you consider feature richness and the other device traits, you can begin to form a more holistic, multi-factor picture of dark patterns in devices. Looking at one trait at a time, one might assume the dark patterns are caused primarily by apps, or primarily by cameras or doorbells, or primarily by Amazon and Google. But if you view all of these factors together, we start seeing that the factors likely influence each other. Larger manufacturers have larger development and design teams and are probably capable of producing more feature-rich products, complex devices like cameras and speakers, and multimodal experiences. So as such, all of these factors impact dark patterns to some degree, but more research is needed to understand the relationships between these factors. So what harms then are implicated by dark patterns in IoT devices? We'll talk about financial harms here, but there are more types in the paper. Now, unlike some apps or website experiences, IoT devices require physical acquisition of the device itself, whether as a gift or purchase, which establishes a financial relationship between the user and the manufacturer. When similar design elements are used in inconsistent manners, they make it harder for users to accurately set product expectations and thus make informed purchasing decisions. Here's an example from the SmartThings app by Samsung, in which the same tile design was used to communicate available features and their status. In this first tile, we don't have any smart locks synced or activated, but as a user, we now know that this is a feature available to us. But the weird thing is that this feature actually isn't immediately available, and when you interact with it, it instead triggers a download when accessed. Prior to this interaction, a user would have no way of knowing that the feature required more on-device storage and an initial download, and that it wasn't available directly out of the box. Similarly, another tile suggested to us that users can get personalized recipe recommendations as a provided feature, but again, this feature wasn't included out of the box. Interacting with it requires users to register with a third-party service, including new account registration and additional consent requirements. So when design consistencies like this mislead users on the strings that are attached for the features or capabilities, users risk spending money on something that can demand more money or data from them later on, just to access features that they assumed were already included. So with these problems identified, how might we mitigate the effects of IoT dark patterns? Again, there's more in the paper, but we'll highlight 2 here. Earlier, we demonstrated that feature richness positively correlates with higher numbers of dark patterns. However, more features shouldn't inherently lead to more manipulative designs. Design loyalty rules suggest that companies should make experiences in ways that align with the best interests of their users instead of disproportionately maximizing the company's benefit. Such rules could help minimize darkness while still creating customer value. Now, to mitigate against the misuse of templated or frequently encountered designs, improved standards can circulate acceptable patterns that promote autonomy and transparency instead of erode it. In particular, such standards make designs more consistent and allows users to set more appropriate expectations for the digital experiences and in particular consumer electronics they might want to purchase. The CCPA sets an example like this for design regulations by providing design standards for opt-in, opt-out buttons, which helps users understand what to expect from these designs. So For greater detail and depth, we encourage that you check out our paper or reach out to our team. But thank you so much for watching.